Good morning, everybody. Thank you so much for attending to this presentation. So today I would like to talk about human-robot manipulability transfer, which is a work that we have been doing during the last years. And specifically, I would like to highlight some of the different aspects that we tackle from a geometric perspective. And we'll see how this impact different kind of components of our work. Let me start by telling you why I think that we should consider this problem of manipulability transfer. If we have a look at this picture, you may recognize that probably the posture of the arm is not exactly what you would expect from an expert that is trying to carry out this archery skill. If you contrast this picture with this one, you might agree with me that this posture seems to be more natural, right? And it looks more natural because the posture is aligned with the direction of motion in which we want to throw the arrow. So this variation of the limbs posture not only happens for this kind of a skill, but we can observe similar behaviors when we want to push heavy objects, or also we want to pull heavy objects. So we usually vary our body posture in order to exert the necessary forces on the objects of interest. So the key message here is basically that body posture is a key component when it comes to perform specific tasks. But this is not necessarily specific for the scenarios that I just described. We can observe very similar behaviors when we manipulate tools or even in sports. And these insights of the influence of the body posture have been also exploited in the context of robotics. So in grasping planning, in reaching postures for humanoid robots, or in hand manipulation. So as I said before, um, all in all, the main message that we want to convey here is that the posture of our body is relevant for a very large variety of manipulation tasks for both humans and robots. So now the question is, given these insights and the apparent relevance of posture in different kind of tasks, how can we transfer posture patterns to different kind of robots that might differ in their kinematic structure? And this is exactly what I would like to tell you in the next few slides. So let me tell you how we start with this work um, by describing first the main component of the framework. So basically the whole formulation is built on the notion of maneuverability ellipsoids, which roughly speaking, in the classical sense, give us a relationship between the velocities that we can apply at the level of the end effector, so just right here at the right part of the slide. And this relationship is not specific for velocities at the level of the end effector at joints, but also we can find different kind of formulations for forces and dynamics, which basically relates the torques at the joints with the forces that we can apply at the end effector or the accelerations that we can also generate in Cartesian space. Here we can see that the ellipsoids basically are telling us the preferred directions in which, for example, we can exert an acceleration or a velocity, or in which we can apply a specific force. And that's exactly what we would like to exploit here. So the manipulated ellipsoid basically is a posture-dependent variable because it depends on the configuration of the robot, and it tells us, with this in mind, the first thing that we would like to do is to analyze different kind of human activities and to see if we can extract some manipulability patterns out of the data that we might collect. So we recently carried out a statistical analysis based on a super cool industry-oriented dataset that was recently released in 2019 by by a group of researchers that did a really amazing job. So basically here I will show you just a really short video on how this dataset looks like. So basically the humans are told to carry out different kind of industrial-like activities like screwing or carrying some objects, and so on and so forth. And what we would like to do with this analysis is to see if we could observe specific patterns in different kind of industrial-like tasks. So, for example, as you can see here in these pictures, the human was told to screw the pieces at different levels to carry different kind of objects from one start location to a specific target and other kind of similar tasks. So in order to analyze um, these motions and these activities, the first thing that we did was to um, come up with a model of the human arm that basically resembles a 7 degrees of freedom manipulator. The idea basically here is that we wanted to extract the Jacobian of the human arm so that we could compute different kind of manipulability ellipsoids. With this in mind, what we did was to observe what was the variation or the behavior of this manipulability in different kind of tasks. So here I'm going to show you a video on how this works for a screwing task where we basically analyze the right arm velocity manipulability of the human. Okay, so the key insight here is that we observe some consistent patterns at the very end of the task, which basically represents the moment in which the robot, sorry, in this case, the human, is executing this screwing motion. The patterns basically look like this. So the ellipsoids are shrinking along the hand axis and are isotropically elongating along the other directions. And this is somehow correlated to the fact that along the hand axis, we require high precision in order to carry out the screwing, but we still need to move in the orthogonal directions. And this basically was one of the insights that we could extract out of this data set. But there are other interesting insights that we could extract. And therefore, then the next question is, how can we use these manipulability patterns in order to transfer this knowledge to a robot, for example? And this is exactly what we would like to do. So given different kind of tasks that are performed by humans, we would like to see if we can come up with a framework that allows us to transfer this to different kind of kinematic change in the context of robotics, of course. So that means that the problem is to transfer task-dependent posture patterns. And basically the main or the key component here is that we are not relying anymore on a kinematic mapping, which could be super hard to solve. But instead, we bypass this kinematic mapping by relying on the description given by the manipulability ellipsoids. So now, let me tell you how we propose the whole framework that allows us to do this transfer between a teacher and a robot. So the idea is that we're going to collect a set of demonstrations from a teacher. This teacher can be a robot, it can be a human, and these demonstrations basically consist of a series of manipulability ellipsoids recorded over time. Important to note here is the fact that these manipulability ellipsoids belong to a specific space, so the space of symmetric positive definite matrices, which can be also viewed as a Riemannian manifold. And this specific view is the one that we're going to exploit in order to formulate a learning framework that allows us to encode a Gaussian mixture model on the space of SPD matrices, and also to retrieve the decided manipulability ellipsoids for specific input data. Now, the problem is that given this learning model and given a decided manipulability ellipsoid, how can we retrieve and control the robot arm or a specific robot platform in order to track properly the decided manipulability profile? And basically, that's the very last part of the framework. So we propose controllers that are geometry aware. So basically that they exploit also this notion of Riemannian manifold theory in order to properly and stably track decided manipulability ellipsoids. So first of all, let me tell you how we learn manipulability ellipsoids in a probabilistic manner. So what we do is that we rely on a really simple approach, which is Gaussian mission model. In this case, we have a joint probability, which basically contains the input. In this case, can be time, it can be the effector position of the robot, it can be also forces. It depends on the problem, right? And then the output basically will be any kind of manipulability definition that you have in your problem. What we do is that we fit a mixture of Gaussians, and we train the model by using a modified version of the expectation maximization algorithm, where we basically exploit exponential and logarithmic maps that are basically extracted from the Riemannian manifold theory in order to properly compute means that correspond to the mean of the Gaussian distribution in the SPD manifold, and covariance matrices, which in this very specific case correspond to 4-order tensors. So I won't go into the details, but I would like to still give you an intuition what's happening here. So here at the bottom, you can see an unidimensional input, and on the right, we can see the SPD cone, which basically represents the manifold in which our manipulability ellipsoids lie on. So we can still initialize our model randomly with 2 Gaussian components, where red and blue represent the means for these components projected in input and output spaces. And what we do is that we carry out an iterative process in order to compute what are the means of these Gaussians in the SPD manifold. And given this, we compute the covariance matrices, which basically belong to the tangent space of this Riemannian manifold. In this very specific case, the tangent space corresponds to the symmetric matrices space. Now, given this model that we have trained, in this case a 2 Gaussians model, we would like to exploit basically conditioning in order to extract what is the desired manipulability ellipsoid that we would like to have for a specific input. So the process works like this. We have a new input, which basically is represented here by our green dot. And we're going to compute what is the closest Gaussian to this input. In this case, is our blue Gaussian. And we're going to initialize the expected output as the mean of this blue Gaussian in the SPD space, so in the cone that you can see on the right. And we're going to implement a similar iterative process in order to update this expected mean. And finally, we come up with an expected output for our manipulability ellipsoids with an associated covariance matrix, which in this case, again, is a 4-order tensor describing the covariance in the tangent space of the SPD manifold. So with this structure, we are able to provide a specific manipulability profile out of a model that was learned from demonstrations. And now the next question is, how can we track a specific manipulability profile, right? And that's exactly what I'm going to talk about in the next slides. So first of all, what we did was to get some inspiration from the classical forward kinematics. And in this case now, we want to basically retrieve a relationship between the manipulability ellipsoid and the joint of the robots. So what we do here is that the manipulability itself is a function of the Jacobian, and the Jacobian in turn is a function of the robot joints. So what we could do is to compute the time derivative, the first time derivative of the manipulability ellipsoid. And basically that leads us to a relationship between the velocities of the joints with respect to changes of the manipulability ellipsoid at the n-effector. And this relationship basically is given by the manipulability Jacobian, which is a 3rd-order tensor in this case. And with really simple math, we can basically retrieve a super simple controller that tells us what could be the decided joint velocities for a given change of manipulability ellipsoids at the end effector. So let me show you, for example, how we could use this in two different kind of scenarios. So here we have a robot that basically is required to match the side manipulability ellipsoid, which is a green one. So here we can see how we can use our controller in order to match this green ellipsoid. And this is for a different case. So as you can see, the robot is able to fit properly the desired manipulability. And now we have a second example where our manipulability tracking is basically projected on the null space of another task. In this case, it's just a simple proportional controller that is trying to keep the end effector at a specific location. So here you will see that the robot exploits the null space to match the desired manipulability ellipsoid. Okay? So there is a key point here, which is the fact that we are exploiting the logarithm maps that are basically specific for this Riemannian manifold that somehow can be understood as a kind of way to compute an error in the space of SPD matrices. I'm going to show you why this is important, so why this geometry formulation is right. So here in this video, we're going to see that when we use just like simple Euclidean-based operations or even a Cholesky-based decomposition, we might end up having really unstable behaviors. So let me show you this. Here we have our controller. It nicely fits the desired manipulability ellipsoid. But then look at the Euclidean controller. Quite unstable, right? And then the Cholesky-based Euclidean controller doesn't do any better. So the key message here is that considering the geometry-aware formulation is crucial when it comes not only to learn manipulability ellipsoids, but to learn any kind of SPD kind of data, and also to formulate any kind of controller to track these manipulability ellipsoids. So now let me show you a couple of experiments that we recently did in the context of manipulability transfer. So this very first video basically uses a Centauro robot in a simulator that initially tracks a manipulability ellipsoid that was extracted from the data set that I previously talked about. And after that, it switches to an end effector position control in order to reach for a specific position here. What I want to highlight here is how this arm is modified in the posture by just tracking the manipulability ellipsoid, and this posture basically is aligned with the direction of the screw in motion without giving any information regarding that beyond the fact that we are tracking a manipulability ellipsoid. A really nice experiment is this one, where basically we are teaching a robot how to unplug a cable with a specific posture requirements, which are basically translated in manipulability ellipsoid profiles. So this was basically in collaboration with some good researchers in the ADAP Research Institute. And here we can see the reproduction of the task. So basically what Baxter is doing is modifying the posture of both arms so that its current manipulability fits the one that is desired, and then it unplugs the cable. What is interesting here is that we can use exactly the same model, no retraining, to transfer this to a different kind of bimanual setting. In this case, two robotic arms to Frank robot. That's what I meant. Exactly the same behavior, posture adaptation to match the desired manipulability, and then unplugging the cable as was demonstrated initially. There are plenty of open points here, right? But one of them is the fact that we don't consider hardware specifications. In other words, we may still need to adapt the profile that we get according to the hardware of the specific student that is trying to replicate this behavior. And additionally, we may have different kind of requirements that are not, for example, task dependent, but could be also platform dependent. So in this sense, it would be good to have a platform that allows us to optimize manipulability in a meaningful manner. And this is exactly the last part of this talk. So Basically, the idea is that we may have at some point to adapt or refine control policies where, for example, our data are maneuverability ellipsoids, which belong to the space of symmetric positive definite matrices. This is not entirely specific for maneuverability, but we can also identify different kind of parameters out there in the robotics applications where the parameters basically lie on the cone of SPD matrices. And the point here is that these parameters that we need to optimize, they don't belong to an Euclidean space. So the very same assumption that we considered previously for learning and control. Note that this is not only specific for the SPD manifold, but we could also find these kind of restrictions when it comes, for example, to encode orientations. So here the point is that if we want to encode orientations using unique quaternions, these unique quaternions basically form a Riemannian manifold which corresponds to the unit sphere. And this is really relevant when it comes to adapt policies in a meaningful manner. What we did was to exploit Bayesian optimization as a framework that is sample efficient to adapt policies in a kind of direct policy search scenario. So there are 2 points to consider here. The first one is that the objective function is usually modeled as a Gaussian process. And specifically, the kernel is the one that is telling us information about the similarity between different points in the space, or the points that we're going to try in order to see how good they are in terms of our objective function. The point is that we don't want to use this Euclidean-based similarity because this basically doesn't measure the real similarity in Riemannian manifolds. What we need to do is to provide a geometry-aware formulation of these distance functions in order to properly have kernels that give us the right information regarding different parameters that we need to test in our optimization process. The second point that we need to consider is that the quality of the next query in the optimization process depends on the optimization of the acquisition function. So basically, what we could do is that we could optimize this acquisition function in a setup that is a constraint optimization. So what we could do, for example, is to say, okay, if my parameters need to be in the unit sphere, I will just constrain my optimization in order to have unit norm for the parameters that I have. But this usually leads to really complicated optimization process. And then what we could do instead is to exploit a geometry-aware formulation of the optimization problem and therefore come up with an constraint optimization. So, a bit more in detail. First thing, our geometry-aware Gaussian process. As I said before, we want to use a geometry-aware similarity function. In this case, we're going to basically exploit the geodesic distance for different manifolds that we might care of. And the point here is that because these Riemannian manifolds are literally curved spaces, then this means that the kernel that we may have is not always positive definite for all the values of beta in this case. So what we need to do is to experimentally determine what is the minimum value of beta for which our kernel matrix is always positive definite. And this is a really simple process. So basically what you need to do is to sample heavily the Riemannian manifold that you need for your problem. But you only do this once because you already know your manifold, and therefore there's no need to carry out this sampling every single time step. You do it only once for the manifold of interest that you have. The second step is basically the geometry-aware optimization of the acquisition function. So basically this is an unconstrained problem, and the first approach that we used or that we explored was conjugate gradient descent on Riemannian manifold. Roughly speaking, this has a quite similar behavior than the Euclidean case, but with some changes that are basically crucial to make this optimization work. So roughly speaking, what we do with this conjugate gradient descent is that we have an initialization on the manifold, and we compute a search direction on the tangent space with respect to this point. So in this case, I'm using the unit sphere just to make an easier explanation or a more intuitive explanation. So given this research direction, we can compute our next iterate zk plus 1 by projecting to the manifold using the exponential map, which is a tool that we use in Riemannian manifold theory. And basically we update the iterate and the search direction in such a way, again on the tangent space. And these last two steps are basically computed in an iterative process until we come up with a next query that we could try in our VO process. So let me quickly show you how this works in a benchmark function, in the active function, which is one of the most used functions out there for benchmarking optimization methods. So here in the video, you're going to see how we're going to start exploring the space. And on the right, we see what is the current best for the optimization process that we have. So you see that around 30 iterations, the algorithm is able to find a really good optimizer for this active function. If we check how this approach works over 100 trials, we can see that the approach that we propose, which is Gabo, provides a faster convergence when compared to the other two approaches. But this was a quite simple setting. So let's have a look at something a bit more complicated. So we wanted to test the approach in a direct policy scenario with stiffness adaptation. So in this case, the stiffness matrix is also an SPD matrix lying in the Riemannian manifold. And what we want to do is to find the best stiffness matrix that minimizes the error with respect to a target that we want to achieve here, while using really low joint torques, and of course by providing a high reward when the position is reached. So here in the video, you're going to see that initially the robot behaves super stiffly, but then as the optimization evolves, the robot becomes more compliant. And basically what the optimization process is doing is trying different kind of stiffness matrices in order to maximize the reward in this case. So as you see, the robot is really compliant at the very end. Again, for example, the statistics that we observed over 15 trials give us not only faster convergence, but also a lower variance solution. And this is crucial because then, regardless of the initialization that we might give to our optimization process, we might still be sure or at least guarantee that the solution will be still bounded in a good regime. So let me finish with what is next with this work that we have been involved in. So the first one is that maneuverability ellipsoids can be exploited for motion prediction. And this could be really relevant when it comes to shared autonomy or to human-robot collaboration scenarios. So we observed that we can easily extract maneuverability ellipsoid profiles. And in the context of human-robot collaboration, we may exploit this maneuverability information in order to extract what are the preferred directions of motion. And that could tell us in advance what could be the set of possible motions that a human or a robot could execute in a short time horizon. Secondly, we could also use the maneuverability optimization framework that I just presented in order to, for example, assist wearable robots in the context of exoskeletons. So for example, here I borrow some images of a really nice paper that proposes a muscular maneuverability that is exploited in order to control exoskeletons, for example, to carry different kind of weights. And last but not least, I really feel that it could be really interesting to exploit this transfer maneuverability for humanoid robots. And indeed, we did some parallel studies on how we could, for example, track a maneuverability ellipsoid at the level of the center of mass for different kind of humanoid robots. So with this, I would like to conclude my talk. Here I provide a couple of web pages where you can check more videos, download our open source code, and read our papers that basically describe all the results that I explained in this talk. And I will be really happy to answer any question that you may have. And you can also reach out by email or in the Slack channel. So thank you very much for your attention. And please be open and don't be shy. Ask any question that you may have. Thank you.